what is, I said got it. Oh, but it's, yes, yeah, sorry. This is not that screen. Of what is a finite product, actually a binary product diagram in the category of sets. And it's called actually a product diagram in general because the category of sets, to get something like that, you use the Cartesian product. And we went through that, and it is what it should be, and it satisfies the property. The condition we went through last time was actually stated for any natural number n, including 0. And in fact, 0 is a bit tricky, just a little bit, because 0 says, hello, 0 says that I'm not considering any objects in the base of the diagram, in the lower level of the diagram, and so requiring n connections requires nothing. It does require so that the domain, that the object, source for all of those non-existing arrows be there. So there is an object, and for any other thing like that, so for any other object, there has to be a unique arrow such that nothing. It turns out that when you read out these conditions in the category of sets, what you need to do in order to get a zero-array product diagram in the category of sets is to take any singleton set, because there is always exactly one function from any set into it. And if you wonder why any singleton set works, it's because the finite product diagram in general determines the data I'm talking about up to isomorphism, but I don't want to go into that. We can go into that, you just ask. It's standard to discover that the notion of product is determined always up to isomorphism. You exchange your opinion about what an ordered pair is in the theory of sets, ZFC, as we've been working in that all the time, and you possibly discover that your idea of an ordered pair is different from that of your colleague sitting next to you. For groups, it's just the observation that on the product of the underlying sets of the two groups, there is a canonical structure of a group which works precisely to satisfy the condition for binary product. Hello. And now the examples which begin to address the question that Marco asked in the exchange of mails after the first session. Take, I hope you remember, the Lindenbaum-Tarski order on well-formed formulas with at most the single variable x3 in the theory with a single unary predicate. O was the name for that theory, if you remember. For the next, that was one. Thank you. And the arrows were just the entailment relation that it was provable within the, well, it's the free theory on that signature. It was provable from a given formula that another formula could be proved, could be derived using the standard rules of. I'm thinking all the time of intuitionistic deduction, natural deduction, but we do not use classical deduction. At the moment, there is no difference. And the condition for given two formulas, the construction of a product diagram on those two formulas consists precisely of the conjunction of the two, because by the rule of elimination of conjunction, there is always a proof from the conjunction to either of the factor in the conjunction, and for the rule of introduction of conjunction, given any two proofs from a single formula of psi of phi1 and another proof of phi2, then one can construct a proof from psi of the conjunction of phi1 and phi2. That's saying precisely, you see, the two rules of introduction and elimination. I'm using them, as I said, my standard will be of having sequence all the time with a single formula on either side. I will never have no formula here. I will never have a list of formula there. I mean, I will have lists of length 1 only. I'm working in the context of a single given free variable x. So here there is a lot of notation missing. Also, for the usual particular case of n equals 0, well, it's required to find a formula, an object in that category, a formula with at most the variable x, so that every other formula can prove it, and the rule of introduction, and also the one which is not there of elimination of the top of the true statement, is exactly what ensures that the terminal, the zero-ary product diagram in that category of formulas is the truth. And now I'm getting to the example of binary products and finite products in general, which really interests us for the next definition. It's the product in the category, in a given category of context for a certain first order theory T. And I'm doing it not just for the general case, I'm doing it for the case of just two contexts with a single typed variable in each. And so the product diagram, given these two, consists of another context. It has to be, well, it's not really very constructive. It is explicit, but you have to be careful about which names one is using here. The best thing is to take completely different variables from those involved here and involved there. So I'm using Z and W instead of something related to X or Y, but one variable has to be in the sort declared here, and the other variable in the sort declared there, you see. And out of two contexts of size 1, we get a context of size 2. And it goes by addition all the time. To check that given any context, any list of appropriate list of variables with given sorts, and given any other diagram with two arrows in the category of context. So what is this? This is an equivalence class with respect to provable equality of terms written in these n variables and producing with those n variables, at least not more than those, producing a term which is of sort S1. And similarly, this is the equivalence class of terms T2 in the variables, producing a term of type S2. That's it. Well, I need to produce an arrow here. So can I see? What don't I see there? Yes, I see one.
Sorry, the screen was just glitching.
Yeah. So I need to produce that arrow, and I'm using the two terms. Luckily, the definition of the arrows in the category of constants are list of terms. Okay, here just because the codomains, the targets of the arrow were of length 1, there was just a single term. But here, I'm interested in hitting a target that has length 2. So I'm giving a list of 2 equivalence classes of terms, and the terms I'm using are exactly the representative of this class and this class that I've been referring to. And well, we've checked it already because it was one of the examples we had when we tested how that category performed. Here you see, in order to check that this composite is the same as that arrow, one has to take into this term the substitution of the variable z with the term t1 and the substitution of the variable w with the term t2, but w is not there. And z is exactly saying, look, take just the first component. In fact, on the other side, there is w. Okay? So formally, essentially, we are just playing with the notation we would use dealing with binary products on sets. Because if I really wanted to define for you the first projection, I would say take a pair ZW and associate just Z to that. And it works. And it's, well, it's not tricky. It's just that one wouldn't think about it if it wasn't tasked. If I have to test if there is also a zero-ary product diagram, well, I just have to check if there is, because I've seen that lengths have matter in products in the form of adding up the lengths. I have to test if there is a string of length 0. And luckily, the sentences of the theory are just those those formulas which have no free variable. And that's exactly the context one deals with mainly when uses when works in mathematical logic. At last, doctrine. This is what I'm going to say is just wrong during the presentation. After you've appreciated this slide, you may leave. We are halfway through the presentation. Yes. So this is blue, and this is a different. I realize now.
Yeah, this is light blue.
Yeah. Because we were wondering before if it was green. This is green. So a doctrine. Now the name doctrine, maybe I should warn you with flashlights. The name doctrine is so nice, especially when referring to things that have to do with logic, that has appeared and reappeared in very different disguises in, well, not just in category theory. So please, if you try something on the web about doctrines, check that they say something which seems related to this page. It may be something completely different instead. Okay, there are at least 3 possibilities that I know, probably 4, but I haven't tested them in the last few days, so I may be wrong, but 3 are there. And but this is the one I'm going to be using. So a doctrine, and this is, well, let's see. A doctrine is a functor D from, well, the opposite of a category. It is a category. Why should I take the opposite of a category since the opposite of a category is a category, and I'm just giving a definition? Because they, well, at least I'm used to the intuition of doing it like that. And I hope I will manage to convince you that there are points in considering not that category, but the category B instead as the basic data. A functor from the opposite of the category B into the category of posets and monotone functions. With 2 conditions, no, with 1 condition, because one I've already said it. The category B must be with finite products. From now on, I'm not going to say product diagrams. I will just say finite products. Yes.
But the functor doesn't have to preserve them.
Excellent question. Thank you. Yes. No request for the functor to preserve finite products. Yes. One wonders, why do I have it? And in fact, it's a question that lingers in the background all the time. It's just that, well, you see, it goes like this. There are variations. I'm very glad that Valeria is still online. She might have gone because I said that, I mean, she understands certainly this slide, so she can leave. But no, ciao, Valeria. And there are variations on this. If I remember, I will address those, but let me go on for a while. So the first argument why a category with finite products and then no request of preserving products is that there are many examples that fit that paradigm, and so why not? The first one, what is called the contravariant power set functor, to distinguish it from the other power set functor, which is the covariant power set functor. But this is in a quote because it's not a name, it's the power set functor. It's the base category is the category of sets, so it has to be a functor from the opposite of the category. Notice the arrow which is depicted in red, because I have to think that, yes, the label is f, so, oh, it's a function, yes, but it's a function in the other direction. So it's a function from the set S prime to the set S, okay? That was the convention I used already the previous time, but then it has to be a functor, and so it has to go preserving the source and target in that way. It maps a set to the poset of the on the parts of S, the subsets of S, by inclusion, and it maps a function, again, a function from S prime to S to inverse image along F. An inverse image is inverse image because it goes in the opposite direction. It takes any subset of A to the collection of elements X in S prime, which are taken by F. Yes, F was function in that direction into A. Okay, that's my definition of inverse image. It's a monotone function. That's all there is. And the category of sets we know have finite products. It was one of the examples. The Lindenbaum-Tarski doctrine of a theory. Now, let's see. Why Lindenbaum-Tarski doctrine? The base category is the category of context. I'm given a theory in first-order logic. So I have objects which are contexts, so they are declaration of variables in the appropriate sorts. To each one of these contexts, one associates the Lindenbaum-Tarski algebra of well-formed formulas, equivalence classes of well-formed formula, improvable equivalence with respect to provable equivalence in the variables, in at most the free variables, xi1, xin, those variables which are declared here. Usually, the Lindenbaum-Tarski algebra of a theory is the collection of all the well-formed formulas with any number of free variables in them. Here, we are slicing up the Lindenbaum-Tarski algebra by considering just the subalgebras of well-formed formulas with those specific variables. I'm writing here an example of a well-formed formula in those variables. It's not how we should write it, it's just phi, because phi is just the notation for the formula with the appropriate variables. But I like the polynomial notation because I'm going to substitute those variables to show the action of the functor from the opposite category. Again, the arrow here is red because I have to remember that what I should be thinking of is the arrow in the category of context that goes in the other direction. Okay, in fact, let me check. It has n equivalence classes, and in fact, there are n variables there, and there are m variables here instead. In fact, those terms are written using these variables in the language of the theory, and there are as many terms as there are sorts in the source in this case, and T1 in that context gives us a term of type of sort, S1, Tn a term of sort Sn. Given those n terms, I can operate with substitution, with instantaneous substitution of the variables xi1, xin with the terms t1, tn. And since the terms t1, tn use these variables, what I obtain here is a well-formed formula in these variables. Okay? Substitution in logic is a nice operation, is a fundamental operation. It goes in the other direction. And possibly this is the main reason why I want to insist on seeing that up there. Yes? Sorry.
Is this propositional or first order?
Any first order theory.
Okay. So if it is first order, should I understand these algebras that what you read as the algebras that are formulas up to equivalence that only use these variables? Or the ones that
free.
Have, that's the free variables.
The free variables.
But you can use other variables.
Oh, yes. Quantifying on as many variables. In fact, I will have the whole set of well-formed formulas on the empty context, and those are going to be the sentences, the equivalence classes of the sentences.
And then the substitution there could be a bad substitution in the sense that
you have to be careful. Yes, you have to be careful. In fact, binding, if you like, maybe the best way is using different variables for binding variables, for bound variables. Another example. This is fun to work with. It's take a poset P and think of it. I mean, that's the way it was presented to me the first time many years ago. Think of P as your collection of truth values instead of 0, 1. And so when you think of properties of a set S, the properties, instead of being possibly true, false, are just possibly a value in P. And so you just declare that you associate to any set S the collection out of subsets of S, out of all functions from S into the poset P. In fact, formally, this is the S power of the poset P with the induced order. So the order is component-wise, it's not lexicographic in any sense. S is just a set. And with this presentation, well, I would expect to have an inverse image function defined there, but it's a lot easier to define it because the elements here now are just functions alpha from S to P, and F is a function from S prime to S. It's read in this direction, it means it's a function instead in the other direction. And so given a function from S to P and a function from S prime to S, I can just compose F with alpha to obtain a function from S prime to P. Okay. If you wonder if the case of the contravariant power set is a particular case of this, yes, but you have to change the notion of power set with the notion, well, with the notion of power, with the notion of exponent with base 2, 0, 1, because it's just that. And it works directly. In all these cases, this functor did not preserve products. In fact, preserving products would mean preserving co-products, taking products to co-products, but we're not getting into that at all. There is an extremely nice example. It was I would say, probably the main one that pushed the notion of doctrine and hyperdoctrine into the foreground, and is that of the doctrine of realizability. And I couldn't fit Plini's realizability here, but it's absolutely that. In fact, the notation intends to almost refer to that. It looks like an example like the previous one, because here I'm taking the power of a poset raised to the exponent s, but I've used not the poset structure here, it's just the set. So the set, the collection of all functions from S into the power set of n with a different notion of order. And the notion of order is this one, which is very nice to read when one think of the intuition that Pliny realized when he introduced realizability of what a proof in intuitionistic logic, in constructive logic, should be. A proof of an implication of phi. I'm sorry, I should say it another word, of an implication of psi from hypothesis phi should be a machine, a partial recursive function, which takes any reason to believe phi to a reason to believe psi. And it is a recursive function that can be restricted to, well, it's indexed by S. So for any S, it takes any element, natural number, because alpha of S is a subset of n. It may be empty, it doesn't matter. It takes any element there to an element on the other side. An element from there to an element there, independent of what the index S is. That happens when there is a partial recursive function that works for all S's. Okay? So there is a complete mismatch here between the reason to perform the proof, if you like, and which is the index I'm acting on. The indices do nothing. It works. It works again by precomposition with F. Then I thought I had to mention, well, in fact, if we get to the final slides, it will be useful. I had to mention two standard examples coming directly from category theory. One is the doctrine of sub-objects. Again, this is pushing the idea that it is right to have to consider categories, base category C with finite products in order to perform the construction of the functor. One has to be careful. One can give the notion of a sub-object of an object C in general in any category. It's a collection of arrows satisfying a certain condition. But then, in order to make sure that this makes sense for every C, one has to be sure to collect all the sub-objects of a given object in a set. And that's not ensured in general from the hypothesis that C is a category. So that is an underlying hypothesis that I have. If you're not worried about dimensions, then fine. And a sub-object is a collection of arrows which are monic or mono, which means that whenever they see two arrows coming from the same object B, and they see that they are equal, then they were actually equal before that. If you like, they turn arrows into identical arrows only if they were already identical and composed afterwards. The condition is one of the elementary conditions that one proves in, I would say, discrete maths 101 to see that injectivity is equivalent to this condition when one works with functions. So it's equivalence classes of this. I'm not going to get into that. If you know, fine. But in order to perform the action of the functor, one needs to have pullbacks in the category. If you know what pullbacks are, fine. It's exactly what I need. In fact, I need pullbacks of monos, but then I already have products in C, and pullbacks of monos and finite products ensure all pullbacks in C. And if you don't, well, you can stop me. But as I say, I just thought I should mention this example. There is another example, which, yes?
Just that previous example.
Yes.
So is this a presentation of the hating category?
This is, no, it's not. It's a hating category requires something. To start with this, you have to have these to be sets, for instance, and you have to have products and pullbacks, but then you need a lot more. Yes, it starts with this, and it's called hating category because you then require this to be hating, and well, you will see them, and these to preserve the hating structure. Okay, and depending on the hypothesis that one has on the category, you can relax a bit of those conditions, but it's exactly the beginning of the presentation. Yes. The doctrine of variations. This again takes into account a quotient. In fact, the quotient which is required by the posted reflection of a category which we've seen last time, and which I'm trying and draw here. Oh, the name variations is the one which appears in the literature. Do I like it? No, I don't like it, but that's the name, and I have no reason to change it. It's not bad, but it's possibly not the best. Can I tell you what the notation for this category is? The category C over little c, where little c is an object in C. It consists of objects which are arrows in the category C with target little c. So these are two objects, X, Y. They have sources. Let's call them A and B. Okay? They're totally determined by the two arrows. So these are the objects. An arrow from X to Y, maybe drawing it there is not a nice notation, but I'll do it anyway. Tell me if you don't like it. Consists of an arrow, K, here, consists precisely of an arrow K in C, such that the triangle that is built commutes. So Y K is equal to X. Okay? It's, I would say it's a construction that you're familiar with if you use families of sets, because families of sets are precisely these, but you may not have seen it like this. So let's take another object, Z, this can be D actually, and an arrow here, sorry, here, which is H. So it is an arrow in C from the object B into the object D, making the diagram commute Z H is equal Y. And I need to define, in order to give the data for a category, I need to define the composition of the operation of composition on these pair of arrows. And I mean, do I have to give it? Yes, thank you. Well, I write it anyway. It's that. And you put these two identities together to check that that arrow, in fact, in C determines something that connects these two. And it's the beginning of the game of commutative diagram pasting, which produces identities out of previous identities. So this is the category C. Now it's a mess. Can I erase this? Well, I leave it there. I redraw the basic data. A, B, the object C. The object C is always the same. A, B, D vary along with the objects of the category C over little c. And this is K. But I will never write K there. There is a very nice name that Peter Fried introduced for this category. He called it the category of commutative triangles, which is nice. But that's not what we use here. That, for the given object little c, is the poset reflection of this category. If you remember what it was a poset defined on the objects of the category, of the given category, so x and y, declaring that x was less than or equal to y, was before y in the partial order relation, if there was a k, there was an arrow from x to y. Which arrow? I don't care. As long as there is one, there may be many, there are probably very many, making the triangle commute, but it doesn't matter. One. We checked last time that the relation so defined is immediately reflexive and transitive. It need not satisfy antisymmetry, so we force antisymmetry. And the category C over little c, poset reflected, is precisely this, quotiented with the relation that forces that to be antisymmetric. So I want to, in fact, take you through the exercise of computing, taking a set S, the poset reflection of this category. Can we do it? So there is the set S. I have to determine a reflexive and transitive relation that I will then turn into antisymmetry. So there are two functions, x and y, from sets A and B, and I say that the function x is before the function y, if there is a function, I call it f this time, here. Any guess? In particular, any guess of when I can say that these two have to be related? So there is a function in that direction and the function in that direction. Mind you, this is a very complicated diagram to consider because one sees two arrows, so one sees, oh yes, that is going there, this is going back, so their composition is the identity. No, there is no hypothesis. Well, yes. Take the function, consider the factorization via the image of the function x, and call J the inclusion of the image of A to x into S. This is surjectives. I have the axiom of choice available, so I have an arrow in that direction, and that's it. Well, I know that this composed with that is the identity here, but it doesn't matter. I just needed an arrow coming back and making the diagram good, yes. And that tells me that a function has to be related by forcing antisymmetry to its image using the axiom of choice. If you try to do a similar construction, say changing set with the category of topological spaces, you think, well, yes, I can do the same thing. No, because now the axiom of choice does not ensure you that the function going back is continuous. You think, oh, okay, I'll use an algebraic structure, I'll do it with groups. No. And in fact, because again, the axiom of choice doesn't show that to be a homomorphism. And in fact, this kind of reversing arrows, comparing one homomorphism with another, are typical subjects of the category of groups, of the category of the theory of yes?
So then this category, the opposite reflection of the R is the category of subsets of subsets of S.
I knew it. Under the axiom of choice.
Yeah.
Under the axiom of choice. What happens without the axiom of choice, I don't know.
And you said that the arrows have the permutations, but no. But it's class of permutations, which is the identity of.
It's going to be no. So
So
the equivalent, but you don't want to. If there is an arrow, that's it. So the reason for introducing a structure is that of considering the homomorphisms between such structures, and finally, one of the reasons to have finite products is that, well, the data consists of a functor, a category, and a fixed category. So essentially, you see me here playing a game similar to this. It's just that I've turned the comma category down here, but in fact, it's slightly more complicated. And so the data to move from one doctrine to another require a way to going from the base category B to the base category B prime with a functor that preserves finite products. And well, and now this is category theory. You have something, you can fit it into a diagram, you use it. I have H, can I fit it there? No, I cannot, because this is B op, but I can use the functor. Maybe you remember we had that example last time. I can use that functor to act on the reversed arrows here, and the arrows that I get are reversed there. So it does fit there by putting an op in. It says somebody, it was, I don't remember who it was, but somebody noticed that the data for H opposite was exactly the same as that of H. Yes, correct. Then is what you test, that it's not the same. And not just that, you want to translate every, can I go back a second? Every poset indexed by the objects, as they call them, as any fiber of the doctrine. Yep. Move any fiber of this doctrine by a monotone function into a fiber of the doctrine obtained by composition. Mind you, there are three doctrines here appearing. There is D and D prime, and yes, we are concerned about homomorphisms from D to D prime, BD if you like, and B prime, D prime, but there is also in the construction the composite of this functor with that functor, which end up being a functor from that opposite category into pos. And I'm not asking that that composition be precisely this. So there are three doctrines. The naturality condition for eta. I don't know, I thought I'd write it down because I always thought it was complicated, but after I've written down, I was wondering whether it was appropriate to show it, but I have it. So I talk about it. Again, I still remember that the arrows go in the wrong direction because I'm acting on arrows in B up. So D, yeah, the arrow appears from B prime to B. So D of X goes from D of B prime to D of B. But when I use X, little x, in the examples, I'll have to think of the reversed arrow because that's the way I presented it. And okay, here. And the naturality condition says that the family eta indexed by the objects of that category is canonical. If I do eta and then the action is the same as doing the action first and then eta. The eta I'm using is different because it changes index, but essentially the family together works coherently on all the fibers. And we'll see examples immediately of homomorphism of doctrines. Again, take a theory in first-order logic and the model, a model, not an interpretation, a model of that theory in the category of sets. So the theory is multi-sorted, so I'm considering a model as a list indexed by the source, the basic source of the theory of sets, M sub S, together with an interpretation for the operation symbols and the relation symbols. Okay, and that's my notation for such a collection of data. From that, I'm going to produce a homomorphism of doctrines from the Lindenbaum-Tarski doctrine of the theory into the doctrine of the contravariant power set functor. And well, essentially, it is just the interpretation of the model as we usually do it. The thing that is actually required to be done is how to define the functor preserving products. I have to go from contexts first, and then I'll have to act also on arrows, but I'll have to go from context, so lists of variables with sorts, into the category of sets. The interpretation tells me that I have a sort, a context, I'm sorry, with a single sort, then that I know how to interpret that variable. That variable is an element of the interpretation M of S1. That's it. But then I have a list variables, and I have a Cartesian product of the appropriate interpretation of the source. Here, the variables have disappeared. If you like, the variables have turned into the arbitrary elements of each of these factors. The same thing happens for the target of the arrow I'm considering, but the arrow are terms. Now, I just have to say it right. List of terms. Each term is in this variables at most, and each one hits the appropriate sort on the other side. So when I interpret T1, say, I know I can semantically substitute the n variables I've used to construct T with an arbitrary, an n tuple in this product, and using the interpretation of the operation symbols, obtain an element there. Because the construction told me that that term has sort S1 prime, and so on. Yes.
Okay. Can we also go back to the previous slide for a second? Okay, so basically, so you can tell me, so the underlying idea here is that because D and D prime, I think,
D prime.
D and D prime,
Yes.
the doctrines are just, you know, some contravariant functions.
Yes.
They don't necessarily, their diagram preserving contravariant. They don't remember universal properties.
No.
So we need specifically in the functor category.
In the functor category, which
natural, the one that beta, natural.
Oh, the natural transformation.
So we need one that remembers the product preserved. We need something that remembers the products in underlying.
I've not mentioned it on the example yet.
Yeah.
The products are remembered here.
I guess that, right, so that is.
It's
right.
just a natural transformation.
Yeah, but it's one induced by a particular.
No, it's not induced. No.
It's data.
So, okay, because that's what I was wondering if it is, so it's just an arbitrary natural transformation.
Yes. Well, so it's exactly a family between posets like that.
Right.
Yeah.
D prime.
No, D of B and D prime of.
So it's a natural transformation from D to D prime composed H up. So it's a morphism, and
I haven't drawn it there, but
there is no.
Right, so you do need to specify.
yes.
Okay. There's a,
Sorry, as I said, and I only said it, this triangle is not commutative.
I see. Okay. So it's just a functor of.
It's a morphism. I mean,
But it
It's
could be a functor between B and B prime that doesn't serve.
certainly,
Right.
but I'm not interested in those.
Right.
Yes,
So we are interested in it too.
yes,
Yeah.
yes, absolutely. And in fact, one of the reasons I was throwing at him for having finite products in the base, although then the second piece of data for a doctrine is not required to preserve them, is because I want to preserve them when I move from one to another.
That's the exact. Yeah.
And if I may force it, the reason why I want it is because I want this.
Right. Or else you wouldn't be preserving deductions.
Well, that will come.
Yeah. Okay.
Because this, again, is only taking care of that bit of definition. I still have to introduce the natural transformation. But I'm preparing things in order to make it work with what I've just written there. Oh, no, I don't have it because I don't have, no, do I have it? Yes, I do have it. Is it here? Yes, it is here. So now I have to give you a natural transformation from this doctrine of well-formed formulas on the theory T into another doctrine, which is not a doctrine of well-formed formulas, but it is still defined on that category. And it goes by first changing the category, I don't know which side to use, changing the category into the category of sets using the definition I've given on the previous slide. So taking a variable, a context with a single variable with a given sort to the set interpreting the sort and taking a list in a context to the product, and then compose that with the power set. So in other words, if I just take the example of a single sort, I will have to connect the Lindenbaum-Tarski algebra on formulas with x as at most as the only free variable into the power set order on the set interpreting that sort. And what it is precisely the interpretation of formulas with at most x as free variable. And I'm thinking of the interpretation, well, I think I have it on the next slide. Yes, I'm thinking of the interpretation as the collection of all the elements, the arbitrary elements in the correct set, which satisfy the formula. And naturality has to take care of matching substitutivity on one side with inverse image on the other side. And here I've actually drawn the test one has to do for the commutative diagram. Start with a formula with y as a free variable at most, interpret it with respect to that sort. So interpret it as the interpretation of phi with the usual interpretation for models of first order theories in a collection of elements of the set ms prime, and then take inverse image with that function. It's precisely this set, which is actually exactly the same thing as the interpretation of phi, where t substituted y in the formula phi. Okay? Another example of a simple reason why every group is a monoid. I don't know. I put it in quotes because it's not a nice sentence to say, but every group has a structure of a monoid. We all know what it is. It's a monoid plus something else. Well, why do we say that? Because there is a homomorphism of doctrines from the doctrine, the Lindenbaum-Tarski doctrine of the theory of monoids into the Lindenbaum-Tarski doctrine of the theory of groups, and not the other way around. Because, well, think of the things one has to do here, for instance. I have to take source to source. Fine, there is a single sort here and a single sort in that theory, so I know where to take it. And then I have to take the basic construct from terms from one to the other. If I start from here and I intend to go there, there is the construction, the operation symbol for multiplication, the zero Ari symbol for the unit, and the unary symbol for inverse. I know what to do with the first two. I have no idea what to do with the third, preserving the properties. And instead, what I've just said shows me that I can do very easily the other way around. I do not care about the inverse because here there is no inverse given. And in fact, what I've just said sets up a homomorphism of doctrines in that direction. And when I take a group, so when I take a homomorphism of doctrines from the doctrine of the theory of groups into the doctrine of the power set, I just compose it with the interpretation, with the translation, because this is actually a translation of a theory into another. With that translation, and I obtain a model of this theory into sets. I don't know if that, well, I'm sure it convinces. I don't know if it convinces you, but it does convince in general. And I'm not going into the details. They are not as clean as I've presented them, but that's the idea. I got involved in this because somebody told me that he understood that doctrines were just another presentation of theories. And in fact, now we are going to go back and forth between doctrines and logical theories. You may not be totally satisfied of the back and forth. I am not totally satisfied, but this is the best one can do. And I'm going to give it to you. So fix a doctrine. And it's going to be fixed for at least 15 minutes. And consider a theory on the doctrine. It's going to be a theory with sorts and with two layers, actually, of conditions. There are sorts. There is one sort for each object of the base category. And then for each arrow in the base category, there is a unary symbol, which is operation of X. That's why I've written it like that, which, when applied as a term, to construct a term to another term of the appropriate type S sub B, produces a term of, I'm sorry, I said type, I had to say sort, of sort SB prime. It depends, I mean, write this condition any way you like in the formal language for logic that you use. This is the idea, and this is the way I wanted to have it explicit. But now we have to remember, and I'm sorry Peter is not here, we have to remember that B was required to
Teacher.
Yeah. I'm not complaining. I mean, I'm very happy that you're all here. I'm sorry, I didn't want to offend anybody. Where was I? Oh, yes. The base category B, we're required to have products. And I mean, there are products among these objects. I mean, there are products among these objects and there are projections among these. So we have written them already. And we have to do something with those. We start with zero-ary products first. So in B, there are zero-ary product diagrams. There are zero-ary products. So there is, what is requested is an object. So there is an object, let me call it 1, because I think of it as having one element in the category of sets. And for that, there is the sort S sub 1. This one is chosen, fixed. And write a constant K with that sort. Add it. I just need that single constant. And then there are all the binary product diagrams, all of them. So take 1 and, well, and here the notation is terrible, and I know I'm going to apologize, but I really didn't know what to do. So boldface P is the product diagram. So it's all these collection of data. It's 3 objects, 2 arrows. The arrows refer, and they all refer to the boldface P here. So the arrows do have a reference to boldface P, but A1, little p, and A2 have no reference. Forgive me. I had to put, I don't know, exponents up there. It got messy, but A1 is A1 of boldface P, little p is little p of boldface P, and A2 is A2 of boldface P, okay? As I said, this is the structure I'm interested in, all of it. It's 5 pieces. So consider a product diagram like that, and forgive me for the, for the notation. Corresponding to the objects P, A1, and A2, there are sorts already in the language, S little p, S little a. A1, A2. Oh, I'm sorry. I didn't know. A is A1. Can I correct it? They're absolutely the same here. I'm sorry, I'm afraid that there are certainly scattered mistakes around because I went copying and pasting. Yeah. So there are these three sorts, and I want, well, there are already, because of that condition, there are already operation symbols, unary symbols for this arrow and for that arrow, and they have, source and target source declared, but then I want a binary symbol which takes a term in the first sort and the term in the second sort and pairs them. And the notation is essentially that of pairing, but I changed it because this is a syntactic notation. Yes?
Or object complete prime and one.
No. This is sorry. I messed it up here in this line.
Not also abstract.
No.
Line.
No. Here I'm saying, well, I want to have an operation that takes anything of the sort of B to something appropriate in the sort of B prime. So for anything in the sort of B, any term, I want something in the sort of B prime. Thank you, and I'm sorry for this. Predicates. The predicates are easy. The properties, the fibers of the vibration, I'm sorry, of the doctrine, the fibers of the doctrine are talking about the logic of the appropriate sort S of B, or Victor B, if you like. And for anything, any object there, I want a denotation for it, a predicate, which will take, it says here, which will produce a formula when given a term of the appropriate sort. Yes.
If I understand well, possibly I understand nothing. This is
Okay.
if I understand well, what you are describing here is the morphology, not the theory.
Yes, it's the first page. Yes.
Okay.
Oh, yes, yes.
This is for
I said 15 minutes. Yes, yes. And unfortunately, I made a mistake. It's a typo which I'm going to pay for. I'm sorry.
Okay, and this is the morphology of a first order theory.
Yes.
Okay.
Well, I still have to give you axioms.
And the sorts of what you speak are not sorts within the same. So you are the sort are from, for example, one sort is a term, and another sort.
No. Sorts. No.
Sorts are no.
Sorts in a many sorted language.
So you are speaking of a many sorts.
Yes.
First order monisort.
Yes. Yes. Yes.
And there is a sort for each object of B.
But then this is a question that appeared also. Jacob was here.
Yes.
You can also make, from a purely syntactical point of view, you can take a second order theorem as a first order, two sorted theorem.
Yes.
You do not need to take the predicate to vary on the subset of the object. And so
No,
you
yes.
can represent a second order theorem also, not necessarily.
Absolutely. I mean, a second order requires two sorts. Well, possibly depends.
Syntactically speaking, there is no difference between first order.
Yes.
sorted
No, it's many sorts. In fact, all my examples were of single sorted theories because that's what happens in first order logic. In first order logic, they don't have sorts, essentially. They have one sort and then they play with the form. In fact, yes?
Sorry, what's the difference between script B and fracture?
This is the category.
Yeah.
And script B.
Smooth one, smooth B, smooth big B.
Oh,
Yeah.
it's a mistake.
Ah,
Clever. I'm sorry. It's another mistake. It's a mistake because after I spoke to you, I decided to use as often as possible the notation. Thank you for reminding me that the notation for small categories, which I had introduced. And I mean, a small category is a category. So essentially, these two, I may claim that they are the same, but it's bad. It's really bad. But the reason why there is a B in fractal mode is because I want to remember, if Marco asked, but he didn't, that I can perform this construction when the collection of objects is a set, because I want a theory. And so I have to be able to tell you that this collection, as b little b varies, is a set. Okay, I'm performing theories in ZFC. If I have a meta theory, then I can do something hand waving, but I mean, I want to work in ZFC.
I have to say that personally, I don't know whether I understood personally, I absolutely do not understand why you need the opposite.
Because I like
the
it.
opposite rather than B. It's not absolutely obscured.
But it's working.
But I have no problem with that. Why?
Because of the examples. Because of the examples. Because all the examples I've given, instead of presenting, let's go back here. All these here, instead of using the category of sets and mentioning sets, I should have say that, well, take the opposite category of sets, which is fine. And then I should have spoken here of a functor preserving coproducts. But frankly, the construction of contexts, for a, I'm sorry, of the interpretation of a context is a product. And yes, it is, I mean, I know it very well. It is a co-product in the opposite category of sets. But I mean, why should I play with the words when the structure which is enforced by the examples is another one? And then there is also another answer to your question, but you should wait. And try, I mean, you cannot.
We should also not wait at 12 more to consider you're speaking for 1 hour 45.
Where's, oh.
1 hour 45. No, 1 hour 15. So.
I can go very quickly through this. I'm sorry. I thought you wanted to know. I'm sorry.
We want to know a lot of things and almost say interesting. But
well, I have
human being. I mean, all the limit of human being.
Well, I can happily skip this if you believe me.
No, I do not believe you. That is what I want to know. So now you make the
no, but then I want to make sure that I answer with the second answer to your question, because doctrines are just a presentation of Grothendieck fibrations, which are amnestic. And Grothendieck fibrations do not require the opposite. It's just that when I present it this way, I have to turn things around. Okay, so there is another presentation which has no opposite. It's more sophisticated. And since we're having problems here, I better get you prepared before we get there. Yes.
Go. That's what I'm interested in.
So I told you that I was going to be cheating a little bit on the first order theory. There are going to be 2 levels, and it's bad to say 2 levels, but I'm going to do it as it is usually done in applications of logic and not really in first order logic. There is going to be this notation. You've seen that there I put 4 bars because I knew there were going to be 3 bars appearing soon. There is going to be an algebraic theory on terms, just on terms. I think, for instance, of presenting the theory of abelian groups, saying that your terms, when you write multiplication, are equal up to associativity. It's a lot simpler, and you write them, and you know it's consistent, and you don't use those equalities in the theory. So that's what's happening. So there is a notion of equality, a theory of just an algebraic theory. So there are just axioms dealing with identities along terms, and then there is a deductive theory on the predicates, on the forms. So first, the algebraic theory of terms. The axioms and rules require reflexivity. V is a variable of a certain sort. This is the separation from the constant from the context to know that I've declared the variables that I'm going to write in the axiom, and the axiom says V is equal to V. Thank you. Then, well, just to make sure that we're talking about equality, here I'm saying that that notion of equality proves transitivity and symmetry from reflexivity. And then there are two axioms. I'll read this first. One says, oh, I've introduced an operation for the arrow, which was the unit on B. I want that operation to act like the identity. So when I apply it to the appropriate variable, it's equal to the variable. Okay? And possibly it's slightly more complicated, but I don't know. Whenever I have a composition of two arrows, well, that gives me an arrow in the category B. So there is an operation symbol for that arrow. Y composed X. Well, I want that operation to be the same as performing force the operation which I had for X, and then on that, the operation that I had for Y. In other words, I want to read Y dot X as if it was the composition of Y applied to X, applied to anything. Okay? And I can say that just with identities. And then if, well, let's read the most complicated one. And then there is, I told you I was going to call it one, and this is another mistake. My God, many mistakes there. This is not a bold-faced one. So I have the constant for the zero array product I've chosen, and I want that constant to be the only thing of that sort. Everything else, V, a variable, has to be equal to that. That's exactly the property that says if V was an element of 1, since it's written 1 there, one is a singleton. And then the three properties for product, and which says that the operation of the first projection applied to the pair gives me the first component, applied to the pair when it's the second projection gives me the second component, and when I pair first and second projection of something, I get that something back. It says precisely that I'm taking care of the little object P as the appropriate product when I use the right thing. And then, well, okay. And then I take care of the denotation of the propositions. I can write, because I have little p and little q in the appropriate fiber, I have, when I substitute a term of the appropriate sort, a formula depending on little p, the denotation of little p applied to the term, and the denotation of little q applied to the term. But if I know that they are related in the order in the fiber, I want to be able to declare that I can prove the denotation of Q applied to V from the denotation of Q or the denotation of P applied to V. And finally, I have to take care of substitution. And you see here, when I write the substituted element of a given little p, I obtain exactly the same thing as substituting into the denotation of little p. And these two are saying that the two formulas are equivalent in the same context, mind you, in the same context. Finally, there are the rules that ensure that the identity imposed on the terms are stable with respect to substitution. And there are these 5 rules. Well, this is transitivity and symmetry together. This is substituting into equal terms. I cannot assume I can prove it in general. This is substituting equals for equals. This is actually the rule of substitution, that the rule of substitution preserves entailment, and this is substituting equal for equals in formulas. Okay? So what are, well, this is what happens. What can I do? I started with the doctrine. I produced a many-sorted theory with that little change with the basic level on identities on terms. And from that theory, I can reconstruct another doctrine. And of course, I want to compare the two. And in fact, the two compare by an equivalence of doctrines. And then one says, well, of course, you want to do it also the other. You want to start from a theory, produce a doctrine, a theory from that doctrine, and compare the two theories. I cannot do it. I do not know how to compare theories. I mean, I can probably translate one theory into the other, but I cannot go backward. There is a mismatch here between what I can do with the structures and what I cannot do with the formal presentations of the theories. The presentations are missing something. And well, the equivalence is actually performed by the standard trick of interpreting each data with the appropriate intention that I've written in the theory. You see, every object goes, well, it has to go to a context. So, okay, I had the sort B, but I'm going to write simply the one sort context, variable V of type S of B, and each arrow has the appropriate denotation ready for it, and I'm going to take that. And I understand you're tired, so I'm not going to go through. Yes. What?
So equivalence of doctrines means that the S functor in particular is an equivalence as well.
Which functor?
The S blank.
The S blank is an equivalence, yes.
So it's like you have a square. If you look at the.
It's an equivalence. It's fully faithful and essentially subjective on objects.
Right, but
in this case.
So between doctrines, it means that if I look at like the proton deconstruction, so
yes.
I get a square, and
yes.
I have an equivalence
yes.
in the base,
and above and above the natural transformations are Cartesian. Yes. I had prepared a slide to convince you that with all those identities which are used here, in fact, one can prove that the object P is isomorphic in this category to the context given by two sorts of SA and SB, the two factors that produce P. I think, yes, I'm sorry I've tired you and I better skip it. The two category of doctrines. So we are start climbing up because now I can use the technicalities of category theory to see above. And it's the obvious definition. I know it's not obvious. I know very well it looks so terrible. But if you've seen anything in category theory, one says, well, give me the two categories, it must be this. Then possibly one says, well, are you sure you want to? It works. You may doubt whether this notation should be in that direction or in the opposite direction because there are so many opposite things, but that's the right thing to do. So it is possible to define. And as I promised, doctrines are particular Grothendieck fibrations. And as you see, when I look at them as Grothendieck fibrations, the base category.
What does amnestic mean?
Thank you for the question. Nobody asked what a Grothendieck fibration is, but it's written there. Amnestic is sort of a pun for near, well, forgetful, yes, for forgetful, but couldn't be forgetful because it's already something else.
So unit, you mean an identity?
Yes. I mean, I've always used unit as a word. I don't use identity because there is the identity function and I don't like it. So it distinguishes unit, which is very peculiar. This is peculiar. I marked it down here because one doesn't expect to have properties like that in a category. So let's see if I can jump back. And so, I was saying, the base category B, now there is no op anymore. The base category B is the same. So given a doctrine, one turns into a Grothendieck fibration by using the same category, but on the other side, and generating an appropriate category T with the functor, which is a Grothendieck fibration with all these things. And the two category, which I had on the previous slide, turns exactly the one you were hoping for, I hope.
Yes.
To see the construction, to see the Grothendieck construction of points performed from the doctrine to obtain the category T, it goes like this. And you see in the picture for the first time that there are directions one way and the other. And this is happening in the base category B, so the arrows go, they're not red, they're going correctly in that way. But when we apply the reindexing functor, when we apply D, then we get actions that go backwards and they fit together to give a category which consists exactly of these two pieces of data. And here, the composition is performed. I just wanted to mention this because I must admit that I prefer much better this presentation to the other I've given. It's just that if I want to go through the examples, and I don't see performing a construction without the examples, this is better. So let's go back to that, and let's look quickly at how the axioms and rules of a theory are not further structure on a logic, but are properties of a logic. A doctrine is called primary. We are going to climb to hyperdoctrines if there is time. A doctrine is called primary if certain monotone functions in pos determined by the doctrine, you see, and this is the poset B, this is the product of the poset dB with the poset dB, it's not D of the poset, D of B cross B, it is definitely not that, and this is just the diagonal monotone function, then there is also this function that goes into the poset on a singleton, and these two arrows, these two monotone functions, are required to have right adjoint in a natural form. So right adjoints to diagonals are exactly the inf of two elements there. So it's exactly the request of an operation of meet with a top element, but the structure which re-indexes along the arrows of the base has to perform correctly with the right adjoint. And a doctrine either has this thing or doesn't. So it's not that I add conjunction to a theory, as we will see. It's just a theory has conjunction, yes.
Are you implying, so is the diagonal, is that the image of the diagonal in B? Are you asking? Okay, so it's just the diagonal.
Just the diagonal function from one poset to the product of the poset with itself. Yes.
So the image posets are semilattices.
The image.
That's what that says. Each image poset, DB, is a semilattice.
Yeah,
but
it becomes a semilattice.
But all those assignments are natural.
Yes.
That's what this is essentially saying.
Yeah.
Thanks.
And it's forced on you by the structure of D.
And it's forced on you by the structure of D because all these choices, well, are not choices, either are there or not.
Right.
Thank you for saying that, yes. I'm going to go through three definitions, and they more or less all look the same. It's called existential, and the reason will be apparent in a second. If some other structure from the doctrine has not a right adjoint, but a left adjoint, the family are natural. Yes.
Yeah, so I was going to, so here you're asking for like the Frobenius. So you're
yes, I haven't asked yet because I haven't got to this line here.
But you're not asking for Beck-Chevalier, or because I was.
It's actually here.
Okay.
Essentially. I'm asking about Beck-Chevalier very softly.
Only, so you mean only for?
Yes, only for projections. Yes.
Yeah, maybe only for the.
We are getting into technical questions here, and yes, I've avoided the mention of Beck-Chevalier because it's not really relevant. And Frobenius reciprocity, I prefer to call it distributive because it looks like distributive.
So I was going to ask about Beck-Chevalier the slide before, but then I realized we weren't talking about, I mean.
Yes, the Beck-Chevalier in general is not available. And it's only naturality all the time. In fact, I'm essentially following Pitt's presentation in the handbook of computer science, or logic for computer science. And there, he tries to use naturality most of the time. Yeah, but
that's the reason why. I mean, yeah, that's the reason why
yes.
You don't need it to be stronger. You know?
And also because the next condition, which is called elementary, requires again left adjoints to certain appropriate monotone functions, and that's the notation for the left adjoint. And again, they have to satisfy naturality condition and distributivity condition. And in both cases, this would be a particular example of Beck-Chevalier condition, and this would be Frobenius reciprocity for that.
Okay, thinking about kind of dialectic vibrations from time to time, I'd like to ask, so the exists for all, like
this one.
Yeah, is there a reason?
No, this is not exist for all, because
no, it's just supposed to.
This is just upside down. After.
Okay, but why?
Just a second. Gosh, you are all in a hurry. I see. Yes, we'll get there. Very good. Yeah, that was to keep you alive. Examples. The power set, the contravariant power set doctrine. It's primary. The inf semi-lattice structure is the intersection of subsets of a given set. The existential structure, the left adjoint, is taking, so here, this is a subset of a product, and it's taking the image on the second coordinate, okay? And it's elementary, and now this goes from from the same poset, but into a totally different poset, and it takes, given a subset of the product of X and S prime, a subset of this product of three factors, which consist of the diagonal for the first two elements, and then in the third component, the other element which wasn't seen for S. Okay? And it works. And possibly I'm going to be able to convince you why it works. You check and it works. In the case of a doctrine from a first order theory, again, the inf semi-lattice structure is given by conjunction. The existential structure is given by existential quantification on the first variable. So this is an example of a formula where there are variables which are bound, and therefore it's appropriately in the Zinder-Bantaski algebra with that single free variable. And the structure of elementarity comes from, again, acting on a formula with two variables by turning it into three variables by ending an identity between the first variable and the one inserted there. Okay, you may wonder why the equality appears all the time, but we'll get to it. The instance of the p-valued sets. Intersection, well, if P is an inf semi-lattice, then it's just pointwise intersection. If P is not an inf semi-lattice, then there is no way to do it. And we know by what you've just argued before. Now, this is not exactly what is required, but if P is a frame, then, there is a P missing there, a sup there missing, and it's the sup on the appropriate indices. And for the elementarity condition, again, it's very similar to what was in the previous slide. It's just that this time the condition for identity has to be replaced with something like Kronecker delta. And that's the reason why the inf semi-lattice needs to have a bottom element. It's required to have a bottom element and write Kronecker delta with respect to that element when S1 and S2 are not equal. Any other element will not do. Realizability. Well, realizability, yes. Here you see the thing that was missing on the other slide. Realizability, it's just beautiful. I don't think there is any point in going through it, but it works. And it's exactly, again, what Kleene did, introducing realizability. Subobject is well, it's a standard construction. And the case of the doctrine of variation, requires a structure on C only to set up the construction. But once they are there, then the weak pullbacks provide exactly the inf construction. But then, in order to get existentiality and elementarity, one just has to use what's already there in the category. It does not require to do anything on the existentialist just composition, and it requires a certain arrow construction for elementary structure. But then, like I did for the base theory when I wanted to discover that there were products described in the theory, I want to do something similar for the various structures in the orders, and so I add axioms. And the axioms I add are precisely those that say, wait, look, when you take the inf of two elements in the fiber, and then you take the denotation of that inf, that has to be the same because these two turnstiles are reciprocal. That has to be the same as the conjunction of formula. Similarly, for the existential quantification and for the elementarity condition, one says, well, look, in fact, it all seemed very complicated. The thing is that there was one particular binary symbol available for you, which satisfied reflexivity, transitivity, substitution of equal in a formula, and the property that two pairs are equal exactly when they are equal component-wise. And it's talking about equality. I think I have the argument for that, but I'd rather just stop here because I want to tell you about the deductive calculus, which has to deal with single formulas on both sides of the sequence. So there is the cut rule, modus ponens, I mean, call it as you like, but mind you, I've not introduced implications, so I can read that as modus ponens. It's a very simple calculus. There is the basic axiom, the reflexivity rule, and then there is a rule of substitution. I'm getting it. I get it.
We did not want our YouTube.
It's going to be.
It can appear.
It's going to be worse than that. I'm sorry. Substitution. Mind you, this is saying that if phi entails psi with respect to the variable v, which appears in phi and may appear in phi and psi, then if I can substitute t in there, I get also this. It's a weak form of universality elimination, but I do not write it with the universal quantifier. And then I have these two compressed rules. Mind you, this is a rule where there is one sequence at the top and two sequences at the bottom. It's just that I write two lines in order to say it's a reversible rule. And this is elimination and introduction of conjunction. And this is introduction of truth and elimination. And with that notation, it's very easy to prove with just these two rules that two formulas can be proved equivalent if and only if either of these two conditions hold, which is explaining why sometimes I can write right rules, left rules, introduction rules, elimination rules. These look like introduction rules, these look like elimination rules, these look like nothing. And skipping the rest, what one would expect precisely is that if I have a theory and I consider the appropriate fragment, which let me speak in the doctrine of over the context of certain bits of structure. So for instance, if I have the theory of local rings, which can be written in that fragment, then I know precisely that homomorphisms of existential doctrines give me models of that theory. So I speak of models, local rings, exactly using the language of homomorphisms, and similarly for elementary doctrines. And finally, this is the definition of hyperdoctrine. I've introduced as a property the notion of conjunction, existential quantifier, and identity. Mind you, I did it very quickly. I didn't notice that, but I mean, there were questions about it. Existential quantification and identity required as a basis the conjunction. The conjunction is there, but not the rest. I can introduce disjunction, falsehood, a universal quantification, implication, and when I have all these properties in a doctrine, then I have a hyperdoctrine. And this was the original definition which appeared in '69. Being Boolean, since I have a Hating algebra here with quantifications, is just another property. It requires that each fiber is Boolean, and here are the examples. All the examples we've been going with through are examples of hyperdoctrines. Some are Boolean, some are not. One further example that I'd like to mention just now is this one, which is a bit on the side. Consider, this is a category which I've never mentioned before, consider the category of sets which are at most of countable cardinality. A product of two countable sets is again countable, so this is a category with product, and consider a complete Boolean, no, countably complete Boolean algebra. So a Boolean algebra just with countable soups, with soups of countable subsets. Then this is a hyperdoctrine because the quantifications I have to do are just controlled by the cardinality level, and these were the structures that were used by Scott and Soloway when they started developing Boolean model for set theory. And starting from these, they got to the models of the negation of the continuum hypothesis. And it needed sets which had control. In a sense, this and this are very different categories. This is essentially a small category. This is certainly not a small category. So we are talking about two very different things. And I'm sorry I will be addressing too many arguments on doctrines, but that's how I could get to hyperdoctrines.
Thank you.
Thank you. Very much. I needed to go to take care of my children.
Oh, I'm sorry. Well, good for them.
Are you sorry for Marco or for the children?
Sorry?
No,
Yeah, sorry for the children.
I was sorry for the children, but then I thought, well, maybe they wouldn't go anywhere. Valeria.
Pino, a quick question, which is very a quick question that's very much the question that I asked Jacopo when he talked about similar things. Everything that you talked about depends on products on the base category.
Yes.
I wanted to do a linear version, so I don't want to have a real product. I want to have a tensor product,
Yes.
not have uniqueness. What can we do?
Thank you for asking the question, because that was the idea I had to mention when Peter asked something similar an hour ago, and I have to get back to to this way of looking at doctrines. So the condition, well, let's talk about a primary doctrine presented like this. So what happens is that both the base B has finite products and the total category T has finite products because they get constructed. In fact, these are precisely the Grothendieck vibrations, the amnestic faithful Grothendieck vibrations, which correspond to primary doctrine. So I take your question to do linear logic, not just in the base, but also in the fibers, okay? And there is a work, the only work that has been done in this part of the hyperdoctrine world by Möller and Vasilakopoulos.
Ciao Pino, grazie.
Ciao. Sorry, Valeria. And they've characterized the amnestic vibrations with respect to a symmetric monoidal structure on B and T, which essentially take care of dealing with tensor products of sorts in the base, but mainly in the fiber, take care of how, with respect to tensor product of sorts, you perform a multiplication in the sense of linear logic in the fibers.
Right.
So definitely the hyperdoctrine approach seems to be applicable to also the linear logic part.
Right. Pino, the thing is, I have done work with Eike Ritter in the 90s, doing a version of that, where the base is Cartesian and the fibers are symmetric monoidal closed categories.
Yes.
And that's the stuff that I was talking to Jacopo about, because, it seemed to me that in that case, we might be able to do a kind of a better job of dealing with the substitutions than the work that, I haven't read the work of Christina Vasilakopoulos,
Yes.
but I kind of worry about other. I'm glad that the only work that you know more specifically about monoidal basis is the one of hers and Moller, right? I don't know who
Yes.
that person is, but because it's not clear to me how this whole thing is going to work out for the equality, because equality in linear logic is problematic, right? You have.
Oh no, I'm not talking about equality. No, I certainly do not know how to address that.
Right.
And I'm not saying I know how to address. I thought you asked how to deal with linear logic, and I know of that application, which is
right.
of
So it doesn't get to the.
But definitely,
yet.
what you mentioned is within that. The work you've done with Eike is within that context, because the base is symmetric monoidal also, and possibly, since to deal with equality you need to speak of diagonal arrows, you need something more than linear logic in the base. I have no idea, so I'm just guessing. And you want something like some kind of affine structure below there.
Well, the way we did it's different, but.
Okay. And it doesn't fit within this.
I think it does. That's what I asked Jacopo to check.
Okay. No, yeah, I don't know. I didn't know that. And I had, unfortunately, Jacopo arrived in Genova the day before I left to come here, so we didn't speak.
Right. Okay.
Okay,
no,
but I'll ask you about this.
it's an interesting idea to try to investigate how kind of starting with the base. I mean, whether just having the monoidal structure on the fibers is good enough for us. That's the question that I have.
I see yes, I see now. Okay.
Okay.
Yes.
Thank you. Thank you.
Thank you.
I mean, it was good. It was good to see despite all the conversations, because it was very good to see you explaining where the assumptions come in each one of the choices. So
Well, yes.
thank you very
I mean,
much.
this is all a lot of old stuff. Yes.
Thank you.
Thank you.
Thank you, beautiful.
No, thank you.
Finally, I know what hyperdoctrine is. I think I know what it is.
I'm sorry. I mean, yeah, I hope you appreciate that I couldn't jump to.
So actually, hyperdoctrine, I had this misconception. I thought that a hyperdoctrine was some kind of a generalization of a doctrine, but it's not. It's a particular, special kind of a doctrine.
Yes, with one care. As I said, when I used for the first time the word doctrine, it depends where you've read the definition of a doctrine in the literature. That definition of doctrine is available, but there are others which are completely different. As far as I know, the only time that a doctrine can be a hyperdoctrine is this case. But the original definition of the Lovia did not go through doctrines. I mean, it got to hyperdoctrine immediately. And then in a subsequent paper, 6 months later, he spoke of doctrines. So whether the doctrines were already in his mind when he wrote this paper, I don't know, possibly.
He used the word hyperdoctrine before the word doctrine.
The word hyperdoctrine appeared in the literature before the word doctrine. I wasn't there. I mean, I was playing football at that time, Italian, European football.
The real one.
The real.
Yes, yeah. Well, I'm a foreigner. I cannot say. Yes. And in fact, if I may add a comment to this, the idea I had, and probably I mentioned this already to some of you, was that Lovia had, since I read this first, I mean, it was obviously coming first, I thought he had this idea, realized after writing about it that it was too complicated, as often he did in his research work, tried to disseminate this idea by reducing it to something simpler in order to get people to get interested in it.
Now here, if we wanted to play the game of the abstraction, we could replace the category pos with the category, and then I guess that similar resource could be obtained. But now things could get I don't know if this if this.
But in fact, that is another one of the definitions of a doctrine.
Yes.
Base can also vary.
But the point is, you can categorify this, and then you get the vibration.
Can I?
I mean, you could put set in there, you would get a discrete vibration, or you could,
Yes, that's the reason why I put this on. I mean,
you could get a vibration.
Why did he?
Like more structure, or you could do something more, more general.
Why did he ask what amnestic means? Because here he didn't want to see these two words.
Mm-hmm.
And that's exactly, in fact, this is what I believe Jacopo spoke about when he was here. But then the things get, well, much more complicated. The fact that we are talking about posets reduce any coherent conditions to non-existent, because it's automatic. Thank you.
Thank you really for preparing this.
It was fun.
Yes.
Can I close?
Yes, yes, I am not sure.
Yeah, I'm glad I double checked the go live page earlier today.